the exactly same time dilation, kinematical time dilation for all these clocks. And the reason for this is actually very simple. The reason is that it doesn't matter whether the clocks are moving with a constant velocity, or in fact, it is the observer that is moving in the opposite direction. The effect is exactly the same. But if the observer is moving with constant velocity, then none of these clocks is preferred. They are all kind of the same to him. So none of these clocks should be preferred in this setting. And therefore, all of them should undergo the exactly same time dilation due to, well, according to this standard Lorentz factor that characterizes all of them. Okay, so this is straightforward. And but we could ask another question. What happens if you, instead of moving with constant velocity, if you accelerate all of these clocks? Suppose that they do not move at constant velocity, but the velocity depends on acceleration. What's going to happen? Well, in this case, in this scenario, you cannot use the same argument that I just used before, because the effect of motion of the clocks is not equivalent to the effect of motion with acceleration of the observer. When observer accelerates, it's a different situation, different physical scenario when clocks accelerate. And that's because motion is relative, but only when you talk about motion with constant velocity. Once you start to accelerate, you can talk about accelerations in absolute terms. Okay, so that means that we cannot use the argument, but what happens to the clocks? How are they affected by acceleration? How is their rate affected by acceleration? And the answer is, it depends. For example, if you accelerate this guy, the pendulum clock, the effect of that is going to be clearly visible because the pendulum will swing at a different rate, because when you change the acceleration, the mechanism of the clock is affected, and the clock will just break. It will not give you the right time. If you take any other clock, for example, a wall clock like this, it is also going to break at sufficiently high accelerations. So the effect of acceleration on each of these clocks is going to be different. For example, if you take an atomic clock, which is essentially a bunch of lasers and a bunch of atoms sitting on top of an optical table, then when you accelerate this whole thing, what is going to happen? Well, all of these clocks will simply fall on the floor, and the clock will break in a spectacular fashion. So you see that all of these clocks are affected in a different way by accelerating them. So the question is, can you characterize in any way, using special relativity, the effect of acceleration on the rate of a clock? And the first answer that we can give is that there is no universality here. Previously, when you move the clocks with constant velocity, the effect was universal, by which I mean that all of the clocks will be affected exactly the same way, and the effect of motion is independent on the mechanism, on the Hamiltonian of the clock. However, when you accelerate the clocks, the effect strongly depends on the type of the clock you're accelerating, and there is no universality here at all. For the same reason, when you place a clock in a gravitational field, it will also...
Yes. Sorry to interrupt you. Can I
go ahead.
Ask a question?
Yeah, sure.
Oh, but this is not exactly related to time dilation. No, is an effect on the fact that the clocks that you're considering are many body clocks. So it's an effect on a many body thing that you are accelerating.
Yeah, yes, you're right.
This behaves differently under acceleration.
I will get to that, and the question we want to ask is whether there exists any clock that, in fact, measures something that is called, time dilation for or a proper time along an accelerated trajectory. And it turns out there is no such a clock, but I'll get to there.
Okay, thank you.
So of course you are. I mean, at this stage, all I'm saying is that none of these clocks are good for measuring time, but they are perfectly fine when you just move them with constant velocity. So the question is, what clocks do you mean when you talk about accelerated clocks? What exactly clock it is? So for example, if you place them in a gravitational field, the effect is going to be the same. Obviously, gravitational field introduces some sort of gravitational time dilation, but if you enhance gravitational field, the pendulum clock will start to the pendulum will swing faster, with bigger frequency, and again you will have an effect that depends on the mechanism of the clock. So probably none of these clocks will be insensitive to that. And the question is, what do you even mean by talking about clocks that measure proper time or measure time dilation and acceleration? So this is the question you want to ask first. And in fact, this has been discussed in literature. This is one of the standard textbook on gravity by James Hartle, and he discusses this exact problem. And what he does, he defines this integral that is known as proper time, which is essentially an integral over a path with the Lorentz factor that is time dependent, because the velocity can be time dependent. Okay, so this is an integral, and now he defines an ideal clock, which is a notion of a device that is able to measure this integral. And the question is whether devices like this even exist, because these clocks that I shown you before, clearly fail the test, because the pendulum clock will break, the atomic clock will break when you accelerate it. Any other clock will be affected by acceleration, but this integral here only depends on instantaneous velocity, but not acceleration at all. So an ideal clock that is able to measure this would be a hypothetical device that is completely insensitive to accelerations. It only measures instantaneous velocity and nothing more than this. And the question is whether these devices even exist. And let me read the comment from Hartle below the equation. He says, it should be emphasized that this formula holds even for accelerating clocks when the velocity is dependent on time. And a famous test of this relation for accelerating clock is described on another page. And let me explain you the experiment that they have performed. So the problems with accelerating clocks is that they have mechanisms that are affected by acceleration, and these mechanisms can break. So the idea is to take a simple clock, one that has no internal mechanism, and the best candidate for that is a elementary particle, a single elementary particle. For example, a muon is an ideal candidate because it has no structure. It's a point-like particle, no different than electron. However, it has a decay rate. It decays within a microsecond, more or less. So if you have a bunch of muons sitting in a jar, then you could use them to measure time by simply counting them and writing the number. That number will depend on time, because the more time elapsed, the more muons will decay. And on average, you can use the average number of muons in your jar to tell you how much time has passed. And it is known that the decay rate of a muon depends on its velocity. For example, muons that hit or are produced in the top layers of atmosphere reach the Earth. And that is only possible because they are time delayed, and the time dilation delays this decay time, and therefore they decay not within microseconds, but in longer times, because their velocity is very close to speed of light. So clearly this is an ideal, this is a good candidate for an ideal clock. The question is, what happens to the muon when you try to accelerate it? And the experiment that was discussed in this other page of the book is exactly the experiment where muons are put in the circular accelerator. They run in circles, and they have chosen the geometry so that the velocity of the motion is really ultra relativistic. It's almost the speed of light. And for that type of motion, if you estimate the effect of centrifugal acceleration, which is roughly of the order of v squared over r, then this factor is of the order of 10 to 17 g for this particular experiment. So they have made an experiment when they took a bunch of muons, they put them in a circular motion so that their centrifugal accelerations was of the order of 10 to 17 g, which is huge. Well, first of all, muons survived this process. They did not break down, so they can move really with high accelerations. And the outcome of this experiment was that it turns out that the decay rate of a muon that goes in a circle for this geometry was exactly the same as if the muon was moving along a straight line with the same velocity. which shows that in this particular experiment, acceleration played no role in the decay rate. So it doesn't matter whether the muon is going in a circle or as a straight line, the decay rate was exactly the same. They found no differences, and therefore they concluded that a muon is a good candidate for an ideal clock because it's clearly insensitive to acceleration, even if accelerations are as high as 10 to 17 G. So the answer that is given by Hartley is, yeah, ideal clocks exist, muons are good candidates, and they measure proper time. Okay, is this clear, or are there any questions at this stage?
For me, it's clear. Thank you.
Okay, good. So now let me discuss these two papers that we wrote a few years ago, where we claim that the conclusions drawn by Hartl and the other authors are wrong. That it is not true that muons are in fact ideal clocks, and that this is only an approximation. And essentially, the claim of these two papers is that no ideal clocks exist, that every device built based on the laws of quantum field theory has to be sensitive to acceleration, even muons. And the reason why they didn't see the experiments is that the muons were not accelerated high enough. If you crank up accelerations, you'd expect that at some point there will be effect of acceleration on the decay rate. And we have studied this in the linear acceleration case and as well as in the circular motion, and the conclusions are the same. Now, let me explain you briefly what is the reason behind this. How is it possible that even muons will be sensitive to accelerations and therefore they will not measure proper time? The key to this is the Unruh effect, which probably some of you may be familiar with, but let me briefly explain what it is. So in quantum field theory, when you look at states of quantum field, these states have properties that depend on the frame of reference. For example, if you look at a single particle, in one frame of reference, it can be characterized by a wavelength that is, say, blue, but for another observer that is moving with constant velocity, the color will be different, will be red, because of the Doppler shift, a very simple effect, known even in classical physics. However, what is not changing is the number of particles. When you had one photon, for example, in one frame of reference, you will have one photon in another frame of reference. The number of photons does not change under Lorentz transformations. However, when you accelerate, and when you consider two observers, one of them being inertial and the other being accelerated, the situation changes. Because for the accelerated observer, not only the colors of your particles will change, the properties, frequencies, and so on and so forth, but also the number of particles will change when you start to accelerate. And the extreme case of this is the so-called Unruh effect, when an inertial observer claims to be sitting in a vacuum in the lowest energy state of the field, and the uniformly accelerated observer will claim that this is not vacuum, there are particles around. So it turns out that not even properties, but even the number of particles and their very existence depends on the observer. And one observer can say there are no particles, and another observer will say there are many particles, and the number of particles actually depends on the proper acceleration of the observer. So the more you accelerate, the more particles around you see. The proportionality constant is very small, so that you have to really accelerate very, very strongly to see anything. But it is estimated that when you accelerate with accelerations of the order of 10 to 19 G, you should already see at least some particles, and their number will be comparable to the, let's say, microwave background radiation, the cosmological temperature. So the Unruh effect is very strange because it says that the concept of particles is frame dependent, and for inertial observers it is not, but when you consider accelerations, the number of particles can be already affected by motion. So how does it relate to the story with muons decaying in acceleration? Well, if you think about the point of view of the muon that accelerates in the vacuum, then from the point of view of the muon, it is not in the vacuum at all. from its own point of view, in its own frame of reference, the state around the muon is not vacuum, but it's filled with particles. In fact, these particles are in a thermal state, and the temperature of that state depends on linearly with proper acceleration. So the more you accelerate, the more thermality around you see, and those thermal particles are of all possible kinds, including muons, electrons, neutrinos, all types of particles, photons, and the presence of these particles has an effect on the decay rate. It is a very small effect, but it's there. And for sufficiently strong accelerations, when you already experienced the Unruh effect, you should expect that the decay rate of the muon will depend on the proper acceleration. So not even muons are in fact ideal clocks, and ideal clocks will always be an approximation. And the conclusion of that is that there is no universal notion of time defined within any operational setting, that operationally the time is not well defined for highly non-inertial frames of reference. You have to pick a specific clock, and that specific clock will give you some indication of the time, but there is no universal notion of time at all. So there is certainly there is no device that will be able to measure proper time, no matter how strong the acceleration is. That was the conclusion of these two papers.
May I ask another question?
Of course.
I mean, if I understood correctly, you are saying that we cannot simply build an ideal clock, and I think that is okay. I mean, it's the same reason why we cannot measure build an ideal ruler, because we need to concentrate too much energy in a single point. So, but the way I see things, the Unruh effect, for instance, it doesn't depend on the detection of the Unruh effect. I mean, it doesn't matter if I can build a detector that is able to measure the particle that is created by the emitted by the radiation, but I mean, it's simply independent of the detector. It's there.
I agree.
If you wanna measure the effect or not is a matter of choice, but the effect must be there for consistency of the theory. The way I see time dilation is the same thing. I mean, the effect must be there. There will be time dilation in any given trajectory you take in a space-time. And this is completely independent of if I want to measure the time or not. Or am I missing something here?
I don't know if you're missing or not, but this is not what Einstein had in mind, definitely, because when he was asked what is time, he said that the time is what is measured by clocks. So you see, it's an interesting question, whether the time exists independently of anything else, or in fact, this is a notion that can be measured, and if it cannot be measured, then it doesn't make sense to talk about it. So I don't know. I don't want to talk about this too much because it's a more of a philosophical issue. I understand your point, and I kind of sympathize with it. So the only claim that we make is that no device built based on the laws of quantum field theory can measure proper time. Now, whether you still claim that it exists in some philosophical sense, I don't doubt. Maybe it's true, maybe it's not. What I'm saying is that you will not be able to measure it. So I leave it up to you to decide how much.
Okay, that's perfectly fine. Now I got your point. That's fine.
But then it's a kind of fundamental problem with GR, because GR is based on the idea that there are ideal rulers and ideal clocks that you can measure space-time positions and times, and you can construct space-time coordinate systems. This is all not possible. This is just an approximation. And
yeah, I agree.
Although quantum theory messes this up because it's not well defined in terms of position or time, it's kind of blurred. But here, on top of that, there is this extra effect that tells you that even if you forget about this quantum indeterminacy and you are looking at average positions and average time, you still have a problem, because for highly non-inertial frames of reference, you can't even measure time on average with any device, which means that very close to event horizon, you won't be able to measure time with any device in a universal way, which is a kind of already puzzling to question the idea of frame of reference at all in the highly non-inertial cases.
Okay, thank you.
So this is the starting point, and so the conclusion at this stage is that when you have motions with constant velocities, you can talk about universality. When you talk about accelerations, there is no universality at all, and you can even question the idea of measuring time with any device that is question the possibility of measuring it at all. Okay, but with quantum time dilation, the story is quite different, because so far we have considered clocks moving with constant velocities or put in a fixed positions in constant gravitational fields. But what about clocks that move in superpositions? So for example, you may have a clock of any type that moves either to the right or moves up, or maybe moves with two different velocities at the same time. We have ways of engineering systems that have superpositions of different momentum states. The question is, can you engineer a clock to be in a superposition of two momentum states? And the question is, what will you see then? And this question was first asked by my former postdoc and a friend of mine from Dartmouth, Alex Smith and Mehdi Ahmadi, and they wrote a paper about this, where they asked the question, what happens when you take a clock and put it in a superposition of two different motions? And they have observed something that was called quantum time dilation. We have then studied this effect in different contexts, one of them being an atom that emits a photon, and we are looking at the decay rate of the atom, or emission rate of the photon, depending on the momentum state of the atom, and we considered momentum states that are superposed. And we have found something that looks like a non-classical behavior. So let me briefly explain what was the reasoning behind this. So you start with a system that we call a clock that has 2 degrees of freedom. One of them is the center of mass degree of freedom, which is essentially the way it moves, momentum state, for example, and some internal degree of freedom that you can call a clock. For example, a 2-level system that oscillates, and you can use that oscillation as the measure of time. What you do next is then you write a Hamiltonian for the system, the joint Hamiltonian, and what you do is typically you generalize a special relativistic formula that relates energy and momentum. Here, we also allow gravitational fields to be taking part. So you have a metric that is non-trivial. And essentially here, this is the mass term, and this is the momentum squared. One subtlety here is that when there is an internal degree of freedom in the clock, that internal degree of freedom can change the internal energy of the clock, which means that it will contribute to the resting mass of the system, which means that you have to take into account the state of the clock to talk about the mass. So that in principle affects the mass term. But essentially, this is a Hamiltonian. This is the paradigm we are working in. And we will consider different settings to study the properties of this Hamiltonian and look at what it tells you about rate of the clock. Okay, so first of all, we consider a state of the clock, the center of mass state of the clock, to be a superposition of 2 momentum states. For example, this could be one momentum state, this could be another momentum state, and we take a superposition with some arbitrary weights and some possible phase. And we consider 2 Gaussian states, Gaussian wave packets in momentum space. So this is one Gaussian momentum space, this is another Gaussian momentum space. We superpose them, and this is how the clock moves. It moves along 2 trajectories with some final width. Now, on top of that, there is a clock degree of freedom that we can use to measure time. And we quantify the amount of time measured by the clock for this input state in the motional degree of freedom versus another scenario in which you start with a different momentum state, which is not a superposition, but a mixture of 2 Gaussian wave packets. So you can either consider this quantum superposition of 2 different velocities or a quantum mixture of 2 different velocities. And the question is whether they will give you the same clock rate or not. The answer given by these 2 papers says that there's a difference, but the effect is not the same. And therefore, the outcome is sensitive to the phase of the superposition. And the Mehdi and Alex called this difference quantum time dilation. And that difference is quantified essentially by the difference of the time rates of these 2 clocks where in one case you start with a superposition of two motions, and the other case you consider a classical mixture. And allegedly there is a difference so that quantum effects contribute to the time dilation. This is the state of affairs after these two papers. And the question we wanted to ask is, to what degree this effect is universal? In the sense that I described before. So how much the quantum time dilation depends on the mechanism of the clock, on the, to be precise, on the Hamiltonian of the clock degrees of freedom. Is it universal? Is it the same for all types of clocks? Or is it going to be different? And so far we are talking about a kinematical effect where the two clocks move with different velocities. This was an open question. We did not have an answer to this. Some case-by-case study suggested that effect should be universal, but there was no proof. And we have asked this question. And that particular question is quite interesting and quite important also for another reason, because people get interested in something that is called quantum reference frames. What is that? When you observe a system in a superposition of two different motions, you could ask a question: what is the point of view of the system itself? So can you introduce a frame of reference that co-moves with the superposed system, and what would be observations taken from that crazy frame of reference where you have a superposition of the different observers? So essentially the question is, if you take the point of view of the clock, will you see the observer moving at two different velocities at once? And such a hypothetical system is called quantum reference frame. One of the paradigms that people tend to take is that there is no difference, that observations from this classical frame and this quantum frame should give you identical outcomes. So the prediction should be equivalent. Therefore, you should be free to use this frame or this frame. The effect should be the same. However, this would only be possible. This universality, I mean, this equivalence would be only possible if kinematical time dilation is universal. For the same reason I just started the talk with, where I talk about a bunch of clocks moving with the same velocity. The reason why the effect is universal is that you could take a frame of reference of the observer and make the observer move, and then that should not affect any of the clock in a different way than the other. So you see that these two things are related, and universality of clocks is a necessary condition for the quantum frame of reference to make sense. That's the kind of short way of putting it. So the question whether clocks are universal or not is also important for other reasons. Any questions or comments? Okay, so let me continue. So is quantum time dilation universal? This is the paper we wrote, and the answer is quite interesting. It depends. Again, let me begin with the kinematical time dilation first. So for that, we take our Hamiltonian, and we take a special case where this Hamiltonian can be actually approximated so that you neglect gravity, you take flat space-time, so that G00 is just 1, Gij is just 1. This is a trivial contribution. And we only consider clocks that are in superposition of different velocities, not two different positions in a gravitational field. Then when you expand this Hamiltonian into some sort of series, you take first non-trivial terms. The first non-trivial term that mixes up momentum degrees of freedom and clock degrees of freedom is of this form, p squared times the Hamiltonian of the clock. Okay, so you have a setup to work with, and then what we do is this. Consider the initial state of the system to be such that the clock is in some fixed state, for example, 12 o'clock or midnight, which is 0, and the momentum degrees of freedom are in some sort of superposition. Doesn't matter what it is. This psi could be a single Gaussian or two Gaussians, doesn't matter. We take a general input state in momentum space. And we assume that these two are separable so that there is no correlations between one and the other. Then we evolve the state And evolution of the state, essentially what it does is it will make the clock age. It will introduce some time delay into the clock, but the time delay will depend on the momentum, because different momenta will be responsible for different time dilations, and therefore the reading of the clock will depend on the momentum. And in general, there will be some sort of entanglement created between these two degrees of freedom. Okay, the next step is that you don't care about the state of the motion, you only want to look at the state of the clock. So what you do, you trace out the motional degrees of freedom and you only look at the state of the clock. So what you get is a density matrix that is in general mixed, because you had some correlations with this other degree of freedom, and when you trace it out, superposition is turned into a mixture. So you get some sort of a state like this, and you see that the general form of the state is of a form that you have a probability distribution in momentum space that is a measure of how you average out your clock states. So this is the probability of finding a clock with momentum p, and this is the reading of the clock. Okay. The next step is that this is a classical mixture, and what you do next is you want to measure time. You want to kind of make a readout of your clock, which means you have to take a clock system, apply some sort of measurement scheme, could be projective measurement, could be a generalized measurements with some P of EMs, doesn't matter. If you take P of EMs like this, the probability of finding a given outcome that I called tau is given by simply this expression where you take a given clock state, sandwich it with your P of EM, and then average out overall momenta. And that's the average, that is the probability of finding the outcome to be tau. And ideally, you'll pick a measurement that such that tau is equal to t, or somehow tau is related to time. But it's up to you what do you measure. And in principle, you could try to measure time, but it doesn't matter. You have to do it. You can do other things as well. However, this is the way it works. This is a general scheme. And as you can see, the probability is given by this simple expression. And I didn't even go into details. I didn't specify what the Hamiltonian is, because I don't care about it really. All that matters is that there is some sort of entanglement that is created here. Okay, so the next thing. What is the conclusion of this? Notice that since the structure of this expression shows you that the probability of given outcome is an average, classical average over all possible momenta of this expression, that shows that if you had a superposition of different momenta in your initial state, the outcome will be exactly the same as if you had a mixture of different momenta. It doesn't matter, because the outcome will be the same. All that matters is the modulus square of psi. So it can be a coherent superposition, but it could also be an incoherent mixture, and the outcome will be exactly the same. So how does it compare with the previous conclusion that there is a quantum time dilation that discriminates between quantum superposition and classical mixture? Well, previously you had a mixture of two Gaussians versus a superposition of two Gaussians. So your classical reference state was a Gaussian. Here, if you take the classical reference state to be a fixed momentum state, then classical mixtures and quantum superposition will give you the same outcome. So this quantum time dilation effect is in fact it is the whole procedure and comparison of your quantum mechanical measurement versus a classical version of it, and it's really up to you what you call classical. You could call classical two Gaussian states being mixed, or you could call classical two momentum state being mixed. Unfortunately, the conclusion depends on your definition of classicality. So that's kind of a subtlety here that we have found. And what about the universality effect? Well, since we already know that classical clocks that move with definite momentum state are universal, so for example, if you pick psi to be a delta function in pi, so that there is just one momentum, the effect is going to be universal, and it's not going to depend on the Hamiltonian. And therefore, if you take a classical average of different momentum states for a clock that does not depend on a mechanism with its time dilation, then this effect also is going to be universal. So the answer is that not only clocks moving with constant velocities give you the same time dilation no matter what the mechanism is, but also if you have a superposition, an arbitrary superposition of velocities, the average measurement of time does not depend on the mechanism of the clock. You can take a two-level system, you can take a pendulum clock, you can take an atomic clock, whatever you take. If you take a given momentum superposition, the outcome is going to be the same. The time dilation is going to be the same. So that is the first observation that we have made. And with that regard, you can say that quantum time dilation is universal. Therefore, you can extend principle of relativity not only to allow inertial frames, but also these quantum mechanical frames that are superposed with different velocities. Any questions or comments?
Yeah, I think I have one.
Yeah.
Okay, I understood what you said, but I'm trying to understand how this can be generalized to a general curved space-time.
Yeah, that's my next slide.
Okay, sorry.
Yeah. So, yeah, but that means you're asking the good questions, because this is exactly what got us interested. So what about gravitational time dilation? You can actually repeat the same thing, the same procedure. Just take your Hamiltonian, consider clocks in two different positions in a gravitational field. And if you take a Schwarzschild metric, for example, the first approximation is that you have a Newtonian potential. You have an interaction in your Hamiltonian between the clock and the position and gravitational field of this term. So you can kind of repeat the same procedure, and eventually you obtain the formula for the clock that again turns out to be a classical mixture of the different position states times the state of the clock. And once again, you will find that the average rates when you make the measurement will be of the structure that you take a clock at different position, at a given position, and then compute classical averaging over all positions with the probability distribution being psi of r modulus squared. And the question,
Yeah, that's my question actually, because when I consider general, let us consider general gravitational field. So how can I compare the energy between two different points, or more precisely, how can I define a Hilbert space in two different points in order to define the superpositions?
yeah, okay, so in general, it is not possible, obviously, because in time-dependent gravitational fields, there is no even notion of now. There is no planes of simultaneity. So you cannot define a Hamiltonian, you cannot define conservation of energy, nothing really, right? However, when you take a static spacetime that has non-trivial symmetries, like killing vector fields,
Okay.
Then it is possible, right? So,
for
I
example,
agree.
I agree.
If you take a like a stationary metric, like Schwarzschild metric, it's a stationary metric. In that case, it is possible to introduce planes of simultaneity. It is possible to define global frame of reference, and therefore it makes sense to some degree. But in general, you are perfectly right. The scheme doesn't work, and nobody knows how to proceed.
Okay. That's my question. So this time dilation that you are showing, it's valid for these sort of space times, highly symmetric space times, where I can define time in at least
look, you have your Hamiltonian, right? You can put anything you want here, right? You can place any metric you want, and this expression should be still valid. And you can ask the question, what happens to your system? How does it evolve with a given metric? But I mean, to what degree this is a meaningful calculation, I don't know. So you can make a calculation, whether it represents some measurable reality, it's another problem. But in principle, the theory is there, right? You can just plug in your metric and carry on. Okay, so here when we talk about gravity, because already in classical case, there was no universality. You have different clocks in gravitational fields and they will give you different time rates because they will be affected by gravitational field. The same happens here. There is no universality for gravitational quantum time dilation because again, you will have a difference between having a superposition at two different heights and mixture of two different heights when you have a Gaussian distribution of position. However, that effect will be sensitive to the mechanism of the clock. Different Hamiltonians will produce different effects. So that is the outcome. So again, gravitational time dilation is not universal. And that also is the case for the quantum mechanical systems. And the last point I wanted to make is something that we have also found that is slightly different. That is that it combines both kinematical and gravitational time dilation. So the question is what happens when you take a clock, make it move at two different velocities and place it at two different positions. So consider a general superposition in momentum and position space. And why this is very interesting because such a scenario has no classical analog because quantum mechanically position and momentum is not completely independent. They give a rise to a phase space, but there is no probability distribution in that Hilbert space. There are only quasi-probability distributions. For example, Wigner functions looks like a probability distribution, but it becomes negative sometimes. So it's not a classical analog. So in general, when you consider a state in quantum mechanical phase space, there is no classical analog of that type of state, which means that you can study the effect of superpositions in position and momentum space, and that will be a genuinely quantum effect with no classical analog at all. And to study this, you have to take your Hamiltonian and expand it to some more terms, to get some more terms that will combine both momentum and position degrees of freedom. And for example, the center of mass degree of freedom, when you expand it, the first terms are kind of separate. This is momentum, this is position. This term combines both momentum and position. This is already interesting. Similarly, when you expand the interaction term, because there's an interaction between the position and the clock, you see there is a clock, and that is multiplied by momentum, by position, and then it's also multiplied by position and momentum combined. So these higher order terms combine position, momentum, and clock degrees of freedom together. They entangle them, all of them, and the effect of that, in principle, is a truly quantum mechanical effect because there is no classical analog of that state. Now, of course, there will be no universality here because as soon as gravity is involved, there is no universality. But in principle, you could ask the question, what is the effect of such a weird superposition to the rate of the clock? And special relativity classical theory will not give you the answer. You have to go to quantum theory. So this is a quite kind of new interesting effect. Another technical point here is that when you expand your Hamiltonian, you have to pick an ordering of your operators, and Hamiltonian itself doesn't tell you what is the right ordering. So, for example, you can pick symmetric ordering, while ordering, or normal ordering, or anti-normal ordering, and that will give you slightly different outcomes. And then orthodox theory doesn't tell you what is the right ordering. So, in a way, you could use this quantum time dilation effect to measure the real ordering picked in nature by real physical systems, because that term will be different for different ordering. So this is interesting in fact by its own, but it also gives you a possibility to measure something that you couldn't measure before, namely how you should naturally order your operators. In quantum optics, we always pick the normal ordering, or in quantum field theory in general, but this is a paradigm that is not well justified. And you could, in principle, measure that in such an experiment where you take a clock, put it in a superposition of the different positions and different momenta, measure the rate, and compare with the calculation. And with that, I would like to thank you for listening.
Okay, thank you, Professor. Are there any questions? Are you listening to me? I think my mic's awful today.
Your microphone is quite low, actually.
I just gotta raise it a little bit. So,
Yeah, go ahead.
are there any questions? Actually got one myself. If you want to, Professor Ferran, to consider like a, if I wanted to consider the same problem you're treating, but now I want to check, okay, what happens if the gravitational field is quantized, even if the linear limit, how would that change? I mean, that Hamiltonian expression that you showed, that would be the same. I mean, only considering a quantum field.
I truly don't know. I have no idea. I don't think there is a universal notion of how to quantize gravity to first terms even. There is ambiguity there. There are even people who say that there is no quantization at all needed. I mean, I have no idea, truly. However, obviously, if there are first terms that you could expand to and pick those terms, then in principle, there is a way to test this with an effect like this, where you actually measure a rate of a physical system and compare it to the calculation. Maybe that's the way to do it, but I honestly don't know.
Okay, thank you. I mean, I probably would have also to consider the dynamics of the field.
The procedure is straightforward. You take your Hamiltonian, expand it into the series, take the terms you like, make a computation with these terms, and then make an experiment, right? That's how you proceed. I don't know what are the corrections here, because what we do here is we work within a paradigm that there is a fixed classical background,
static metrics,
fixed classical trajectories, and then on top of that, there is have quantum field theory. Or not even that, even not necessarily quantum field theory, even first quantized picture is also fine here. So if you want to go beyond this, I would be shocked if there were any corrections in these regimes. I would expect corrections in higher order terms, but this is still far beyond any experimental capabilities.
So, yeah, sure.
My intuition, if I was to guess, would be to say that first terms will be the same, but higher order terms will be different.
Oh, okay. Okay, well, thank you. So
talking about experiments, I mean, how to measure these things in an actual experiment, or at least if it's possible to simulate these, to build a simulation of these, a quantum simulation, things like this.
So this paper was actually aimed at trying to answer this question, because we have taken a model of an atom, an actual atom, not a kind of a Mickey Mouse model, but an actual atom that emits a photon, and we have taken the full Hamiltonian of the atom, added positional degrees of freedom, and consider a motion of the atom and look at the dip of emission rate of a photon, which in fact is not very hard to measure, because instead of measuring the emission times, you could make measurements of emission spectrums. And spectral measurements are very precise. And in fact, they are one of the most precise measurements that can be carried out. And we have shown that the spectral properties of the emitted light depends on the motion. And in particular, when you take a superposition of the different motions, that has an effect on the spectral density of the emitted photons. So the proposal was that, in fact, you could try to measure, this would be the easiest way to measure this. Take an atom, excited atom, make it move and measure the frequency of the light that is emitted. And we have computed exactly how the spectra are affected by the initial state of motion. And in fact, Alex, who is one of the proponents of this idea, he spends a lot of time talking to experimentalists and trying to convince them to look at experiments.
So is it possible to actually measure this with current technology?
That's
nice.
It's quite close, yes. So in this regard, this is an effect that is kind of promising, because the reason is that you have, on one hand, you have very precise atomic clocks, and you have extreme precision of measurement of time. On the other hand, you can already create superpositions of motions for small systems, and you already at the regimes that are available, you should be expecting some effects to happen. So Alex is looking into this intensely, and he believes that this is within a reach.
Okay, okay, that's nice.
Okay, so is there any more question? Well, I would like to thank you again, Professor, for accepting the invitation and for the talk.
Thank you very much. It was a pleasure.
Well, thank you very much for the excellent talk.
Thank you so much. Thank you for inviting me.
Amazing.
I've never been to Brazil. It was a pleasure to be there first time.
Well, this can be arranged easily. Actually, Thiago will spend 1 year in Gdansk,
Oh, really? Yeah.
starting in September.
Yeah.
Okay. I'm visiting there with Horodecki's probably, yes?
Yeah, with Łukasz Rudinik at the institute
Okay.
there.
Okay, yeah. Yeah, I know these people. I mean, they are friends of mine, so